And now we're going to conclude section 3.2, which is the algebra of continuous functions. Now recall, we just saw in the previous video that cosine of x is equal to sine of pi over 2 minus x. So if f of x were equal to sine x, and h of x were equal to this thing right here, pi over 2 minus x, we can see that g of x, which is cosine x, is f of h of x. Remember what that means. You're taking the function f, and in place of x, you're plugging in at pi over 2 minus x. So this becomes sine of pi over 2 minus x. And we write this composition of functions like this, although I actually prefer it this way. This means f of h of x. Therefore, cosine x is the composition of two continuous functions. And cosine x is continuous. So it turns out that if you take two continuous functions and compose them together, the new function that you get is also continuous at the appropriate domain. So the values of the real numbers that make sense for that composition of functions. And that's what theorem 3.4 says. Let's let f be a function from the domain capital D into R. Let g be a function from D prime into R, where f of D is a subset of D prime. I've kind of got that sketched out. Let's go ahead and finish the statement of the theorem. For some x in the domain x naught, if f is continuous at that x naught, and if g is continuous at f of x naught, then g composed with f is continuous at x naught. So this is just a reminder if you haven't seen composition of functions in a while. I know we've seen it recently. But all three of these sets pictured by these oval shapes are subsets of the real number. This is our domain D, the domain of the function f, and it maps into, let's see, f of D, which we have also called the image of f. It's the set you get when you map all of these numbers by function f. It comes straight over into this set here. That's the image of f, or f of capital D. It's a subset of some set D prime that we're not going to worry about. And then the function g goes from D prime, this whole set, into some subset of the real numbers. We're calling that the image of f. So basically these numbers out here, we don't need to worry about them. When we do the composition, we're going to take some point in here, say, call that x. That's going to get mapped to some f of x over here, not outside here. And then we're going to take g of f of x, which is going to put us somewhere in the image of g. So that's the picture. I'm going to erase that because I'm going to try to squeeze the proof in here. Okay, so we're taking these two functions as defined, and it doesn't say that they're continuous functions. That would mean continuous over their whole domain. It just says that this function f is continuous at x naught, and that g is continuous at f of x naught. So we need to prove that g composed with f, g of f of x, is continuous at x naught. So if we want to show continuity, let me get back to the purple, continuous function, I need an epsilon. So we're going to start off with let epsilon greater than 0 exist or be given. Now I'm going to take a delta 1 greater than 0. Let that be such that y Now let me first make sure y is in the domain. Y has to be in D prime. And y minus f of x is 0, some other number, less than delta 1, implies that g of y minus g of this, g of f of x naught, is less than epsilon. Okay, we're allowed to do that because we know that the function g is continuous at f of x naught. So if you want to write the explanation or justification, this delta 1 exists because g is continuous at f of x naught. And this looks a lot like the definition of continuity at x naught, at f of x naught. All right, now we need a delta 2, a two-step process here. Let delta 2 greater than 0 be such that x in the domain here, that's going to be our starting number, x in the domain, and x minus x naught less than delta 2 implies f of x minus f of x naught is less than delta 1. This number right here. This is the same as that. Well, we're almost done. About one more long sentence and we'll be done. Again, we didn't justify this. I didn't write down the justification. Why does delta 2 exist? Because I know that f is continuous at x naught. Therefore, that's true. This kind of takes the place of our epsilon in the definition. All right, thus, let's just rewrite this right here. X in the domain and x minus x naught less than delta 2 implies this. Less than delta 1. Well, if you take two numbers less than delta 1, the distance between them less than delta 1, this corresponds, now this is true. F of x is just equal to y. So now we get this. We get that g of this minus g of this is less than epsilon, right there. So g of f of x minus g of f of x naught is less than epsilon. And that completes the proof. And so maybe I'll say, and therefore, g composed with f, g of f of x, and I'll put in brackets here, i.e. g composed with f of x is continuous at x naught. And that's the end of the proof. One final thought. This tells us quite a bit of additional functions that are continuous. I really ran out of room here, but maybe I'll use a different color and just say that functions like this, continuous functions. How about sine of cosine of x? The composition of sine and cosine. So one similar to one we saw a little bit earlier is something like cosine of x to the third. X to the third is a polynomial function, continuous on R. Cosine is a continuous function on R. This is a continuous function as well. And we could then say cosine of sine x squared and so on. We can make all kinds of combinations of functions. And if the two initial functions are continuous, then the composition will be as well on its appropriate domain.